Hey guys, what's going on? So today we're going to be talking about physical chemistry, right? So in our last video, I talked about going into hyperproduction mode. That's exactly what I intend on doing. PChem is going to be every Tuesdays. Chern-Simons theory, I'm going to continue every Mondays. And I'm sort of establishing a schedule for everything else. Also, I have so many ideas I want to start bringing forward. Any contribution that you guys make to this channel is going to go directly into putting more content into this channel and eventually making a website for this, because this is really something that I'm very interested in doing. And so with that being said, make sure to hit the like and subscribe button. You can become a member here on YouTube, or you can go onto Patreon. Now let's get straight into PChem. So this is how I'm going to introduce many of the future videos to come. So in this particular one, we're going to be going over a book, and that book is this one, Physical Chemistry by McGuire and Simon, John D. Simon. I don't know if you can see that, but this is the book, and it's a pretty thick book. Okay, my aim here is to do a chapter per week. It might be a little bit daunting, but I've gone through this book already, and I sort of know it pretty well, and so. Yeah, and I have some on the back burner as well. So this is the book. If you don't have the book, it's okay. I'm gonna go through it in detail. If you do, you can follow along. I'm not gonna be following it word for word, but I'm gonna be condensing this down into videos that you can easily digest and understand. And so let's just go over the syllabus, if you will, for this really quick. So for the first week, we're going to go through this dawn of quantum field theory. This is the first chapter, right? So we're going over a chapter a week. Next week it's going to be a classical wave equation. Then we're going to go through the Schrodinger equation and particle in a box model. And then we're going to do some postulates of general quantum mechanics. We're not going to go deep into it. In this playlist, we're not going to go deep into quantum field theory or anything like that. We just want to know the quantum mechanics necessary in order to do PChem. And then the harmonic oscillator and the rigid rotor. These are two iconic models that we're going to use to understand molecules from a physics perspective. And then the hydrogen atom. This is the iconic model, or the iconic example that everyone goes through, not just in PChem but also in quantum mechanics, because it's really just a two-particle system, a proton and an electron, and then we scale up from there and do approximation methods after that, okay, for larger atoms and larger systems. And then that's going to ease us into multi-electron atoms. Pick an atom, right, and we're going to try to model these atoms in the physics and try to understand the orbitals and all of that, all the PChem, or all the quantum mechanics needed to understand the dynamics of these multi-electron atoms. And then we're going to go into the chemical bond, right? So the chemical bond is quintessential in chemistry, the idea of the covalent bond or ionic bond. So we're going to go into this in quite depth. Diatomic molecules, this is stuff like N2, O2, H2, all of this kind of stuff. And then polyatomic molecules, so polyatomic, multiple atoms, not just diatomic. And then computational quantum chemistry, we're going to go over some of that. We're not going to go deep into this. We're just really going to cover what the book covers. And then we're going to do some group theory, again, not super deep into group theory. We're going to go a little bit through some problems of symmetry, homomorphisms, isomorphisms, and all that kind of stuff as well. And then we're going to do some molecular spectroscopy, and then NMR, nuclear magnetic resonance spectroscopy. We're going to dedicate some time to this as well. Again, these are really just the titles of the chapters. Lasers. Laser spectroscopy, properties of gases, Boltzmann factor, and the partition function. So by week 17, this should be, this is starting to get into statistical mechanics. Okay, the partition function, ideal gases, And then first law of thermodynamics, the second, the third law. We're going to go over concepts of entropy, Helmholtz and Gibbs energies, phase equilibria, and solutions, chemical equilibrium, and then kinetic theory. And this we're going to go through the physics of all this, right? So we're going to try to understand equations, right? This is the math and the physics of all of these very interesting things, and we're going to be able to understand chemistry at a much deeper level because of this playlist. So let's get straight into the dawn of quantum field theory. Oh, and then we have some more, right? So chemical kinetics, rate laws, reaction mechanisms. This is getting into in general chemistry, right? In general chemistry, when you learn about rate laws and reaction mechanisms and all this kind of stuff, you're really just presented. It's really just presented to you as this is what happens. This is what you have to know. Here in PChem, we want to dive deeper into that. We want to say why. Why does stuff like this happen? Why do we have a rate law, for example, for some chemical reaction? Why do reaction mechanisms happen the way they do? And we're going to try to understand that from the perspective of physics and PChem. Gas phase reaction dynamics, and then solid and surface chemistry. And we're going to go into these in quite depth because, again, we're going to go over a chapter a week, and when we do, at least we can aim for a chapter a week. There might be a week I skip just because I'm too busy or something like that, but I'm going to try to keep it up. And then, again, more support on your end is going to give me more ability to dedicate to this channel. Okay, so without further hesitation, let's get into chapter 1. Again, chapter 1 is the dawn of quantum field theory, or not quantum field theory, the dawn of quantum mechanics, if you will. So that's quantum theory. So in this video, we're going to go over the following topics: blackbody radiation, photoelectric effect, the hydrogen atomic spectra, Bohr's model of the atom, and Louis de Broglie's insight. So let's start off with blackbody radiation. Okay, so there have been many attempts to explain the decrease in intensity values of increasing frequency radiation from a blackbody. So a blackbody you can just think of as a box, and this box, when you have so let's just look at this, right? So this is the frequency of light that's being emitted from the black body, and then the intensity that we measure. And what happens is that you would think that as the frequency of light increases, the intensity should increase, but we actually get this decrease here. And this decrease here was the big question quite some time ago, during the 1920s, when people were starting to get into quantum mechanics, people like Einstein, Bohr, Heisenberg, and all these guys, and they looked at this data, and they told themselves, how can we model this? How can we understand this? Because as of right now, to our intuition, this just seems like these two things should go up together, and there shouldn't really be any decrease. But we're seeing a decrease here, so how can we explain this? Well, the first attempt at this was made by Lord Rayleigh and J.H. James, but this only worked for low frequency values. So the match worked for these frequency values, but not like from here, like right from here to here. But beyond that, there was a huge divergence, and you could see that. So this was the model that they had made, and there was a huge divergence there. And this ultraviolet catastrophe, the catastrophe being that it diverged completely away from experimental data, was modeled by this equation, okay, where the radiant energy density was the intensity here, between frequencies nu and nu plus d nu. Here's d nu and here's nu. You can see this is exponential. This is squared, right? So that's why there's this huge divergence, but then there's nothing in this term that causes it to go down like this. And so, hence the ultraviolet catastrophe. And then there's all these constants in here. We're going to get into that as well. So because of the ultraviolet catastrophe, there was an attempt to account for this problem because for this problem in our calculations. And so in comes Max Planck, and he found out that if he were to assume that energy came in discrete packets, then he could generate an equation or calculate an equation that matched this data. And here's the equation, right? So instead, he had a cubed factor in here, but then he had nu also in the denominator here. So it being in the denominator here is going to repress those values as they get bigger and bigger, because as nu gets bigger, the exponent here gets bigger, but the denominator in effect gets smaller. And so at some point nu, there's going to start to be this drop. And this equation gave us exactly that. For the data to match the value, he determined that h, this value h here, had to be 6.626 times 10 to the negative 34 joule seconds. And so this is a famous Planck constant. It sort of came out of attempting to understand blackbody radiation. So let's continue. With Planck's new equation to describe the radiation of black bodies, we can now calculate the point at which the peak occurs with some rudimentary knowledge of calculus. So again, I'm not really assuming that you know calculus, but I sort of am, right? So a lot of this, there's going to be a lot of calculus involved here. I'm not going to start from square one. So there's going to be calculus involved. If you don't know calculus, if you're interested in me going over a calculus playlist, I would be more than happy to do that. I've taken calculus a long time ago, so I'd be willing to do that. It just might, it hadn't really occurred to me to do that yet, but I'll think about it. So here's our equation. This is our equation. And then we can get from here to here through this relationship, right? So there's an inverse relationship, again, between the frequency and the wavelength of some particular wave, and that relationship is given by the velocity of that wave. And when we're talking about light, the velocity is c. We can then divide both sides by this lambda, right? And then we could take the derivative with respect to lambda. Right, so, and that's how we get this minus 2 in the exponent here, okay? And then the negative comes out here. And so, to get from here to here, we use this, right? So, let's see here. So, C, we're going to replace C. You can just pause this. I'm not going to go through this in great detail, but we use this relationship to get from here to here, and then to get from here to here, we are going to divide both sides by this guy, right? Or take the derivative, right? So we're taking the derivative of both sides, right? So taking the derivative of this with respect to lambda here, taking the derivative of this with respect to lambda right here. All right, so when we take the derivative, a lot of these guys are constants. And we're going to set the derivative to 0 because, again, when we're doing this, the goal here is to understand what this peak value is, right? So, and there should only be 1 divided by sign. I'm going to take the thickness of my pen. I'm going to take there should be only 1 divided by sign right there. And so here's our constants. Right, so to get from here to here, I'm literally just taking the derivative, and then from here to here, well, that is, we're putting max here because we're setting this equal to 0. And you can stare at this long enough to get from here to here. This is really just the product rule, right? So we're taking constants out. And then the derivative of this, well, we get the negative 5 from this exponent here, and we drop the exponent again. And then, so it's that, let's see, times this here, right? And so we're calling all of this x for right now, just to condense a few things. And then the derivative of this times this here, right? So this here is going to be this one, and then the derivative of this is going to be this guy right here. And then to get from here to here, we get this, right? X being, again, all of this stuff, all this stuff in here. All right. And so now we have an equation in terms of x that we could solve. So we could solve for x, right? So when we solve for x, we get this. So this value here. So x in this equation is x equals 4.956. And you can just use like a calculator to do that if you want. And so this is x, right? That's what we're saying. We're saying that is x. And then to get from here to here, right, we're going to multiply both sides by kb. Here's that, divide by hc, and so we get this. This was the first hint. So this is this was the first hint that energy was quantized in packets that were going to be called quanta back in the 1920s and 30s. In treating energy as a quanta of energy, or billiard balls, which is what Planck did, he was able to generate this equation which perfectly modeled the data for blackbody radiation. Later, Einstein is going to use the same assumption to accurately predict the behavior of electrons emitted from a metal surface, and this is the photoelectron effect, or photoelectric effect. So the photoelectric effect, for a while, physicists thought that the intensity of the heat of a metal surface was proportional to the square of the amplitude of the electromagnetic field that radiated from the surface. However, this did not concur with the observation that there seemed to be a threshold of intensity at which the electrons were ejected. By assuming that energy was quantized, Einstein managed to accurately show that there was a work function that identified this threshold. So the kinetic energy of some electron, he said, was equal to the frequency times the Planck's constant minus some work function, and that work function is going to be the Planck some frequency again, some initial frequency times Planck's constant. So you could sort of think of this as all the billiard balls, or all the electrons in the metal surface, are sitting there, and you're bombarding increasing amounts of radiation of increasing frequencies at the metal surface, and they're not budging. But then at some point, you increase the frequency to a point where electrons start getting emitted, and you're able to detect those electrons. And so that point of frequency is the point that is identified as the work function for this particular metal surface. And this work function is different for different metal surfaces, okay? So the idea here, again, is that we're treating electrons as billiard balls, okay? In one case, the assumption of the billiard ball helped in establishing a model for blackbody radiation. Now it's helped us in understanding the photoelectric effect. Let's continue with Bohr's model of the atom now. So the predominant and most relevant model in all of chemistry and all of physics is Bohr's model of the atom. He proposed that the atom was organized with a nucleus consisting of protons and neutrons at the center of concentric orbitals consisting of electrons. So just as an example, his model was proposed to look something like the following. So this is just phosphorus, for example, right? So phosphorus, we have 2, 4, 6, 8, 10, 12, 13, 14, 15 electrons. So electrically neutral phosphorus. And this is what it looked like, right? And if we can zoom in here, we have protons and neutrons and all the good stuff. Okay, so when energy is absorbed by an atom, the proposal was that energy is coming in, electron takes that energy, gets bumped up to some energy level, and then as it's falling down, it emits radiation. And let's ask the question now, what is the energy? What's the energy of this one of these particular electrons? Now we're going to do this for hydrogen, not for phosphorus. I just made this model for phosphorus just to add a little bit of complexity to here. But let's just do this for hydrogen. For hydrogen, we're going to have Q1 being the charge of the proton and Q2 being the charge of the electron. Okay? And so the potential energy here is given to us by Coulomb's law. The kinetic energy is given to us by this equation, by this formula, 1/2 mv squared. And the charge of the proton is equal to the charge of the electron, just different signs. And because the electron's negative, this is going to become negative. And so to get from here to here then, again, if you don't want to hear me talk, you could pause, write this down, mill in it if you will. And so I'm just talking through this to be more complete. I want to go through this whole book, and I want to feel like I'm doing a complete job on this. And so to get from here to here, right, we're just factoring out the 1/2 and the 1, right? And so we get minus 1/2 k e squared over r. So let's stash this in our mental log book, because, and to get from here to here, right, so we're also treating the centripetal acceleration of the electron around the nucleus is equal to the electromagnetic force as well, or the Coulomb force, right? So the Coulomb force is this guy. Again, charge of the proton, charge of the electron are equal and opposite. But here, since this is a force, we're just concerned with the magnitude, which is why we don't have a negative here. And so to get from here to here, again, we are just, we're multiplying both sides by r, right? So then we take this, put it into here, and that's how we get this. And then we can do the rest of this and get down here. All right. We can also take a look at the angular momentum. The angular momentum here is mvr, right? So the mass of the electron times its velocity times the radius at which it's traveling, right? So the radius, again, is the radius from the center to where the electron is relative to the center. MVR, so the angular momentum is quantized. We're going to propose that it's quantized. And so it's quantized by Planck's constant, with Planck's constant being, we have h, and then h bar is equal to h divided by 2 pi. And then we get this here, and then to get from here to here, we are, let's see, so to get from here to here, we're just dividing both sides, and then to get from here to here, we are putting this guy into here, right? So, and we get this. To get from here to here, then we get m. So this stays the same. This, did I do anything different here? N h bar mr squared. I did not do anything different. From here to here, then, we're just squaring everything. Then from here to here, we are canceling m's, right? We're able to cancel some m's. Cancel m's. That's catchy. I kind of like that. So we cancel the m's, we get, and from here to here, then we're just isolating r, right? So multiply both sides by r, divide both sides by ke squared, we get this guy. This is the Bohr radius right here. So we've derived the Bohr radius. Let's keep on going, because we want to get to an interesting equation called the Rydberg equation. So we now, so to get from here to here, right, so we logged this guy in the back of our head. Let's take this guy now and apply it. And we get this, and then to get from here to here, we have n squared, and then all these other factors come out as a constant. And here, these are the energy levels for the hydrogen atom. So whenever an electron gets ejected into some, or absorbs some frequency of energy and gets bumped up to another energy level, those energy levels are identified like this. So E1, the first energy level, it's going to have this energy. E2 is going to have this energy where we put 2 in N. E3, and then so forth. So all of these energy levels have a particular energy to them, and we can calculate those energies. So we now use the fact that the difference in energy between the two energy levels is this guy here, right? So the initial energy, the difference between the initial and the final energy state is going to be some frequency, right? Because as it decreases, as the electron is here and it falls down, that's the frequency of this guy right here. So here, this is going to, so H bar, again, H bar is H over 2 pi, right? So we have the 2 pi H bar because this guy is going to condense back down to that guy, right? And then we have this here. F is just the speed divided by the wavelength, the frequency for speed divided by wavelength. And then, so we can isolate this even more, right? So the difference between the two energies is equal to this divided by this. And then the difference between the two energies, well, we said that the energies were here. So initial, final, these are two energies. And then we can take out these constants, right? So here's these constants here, these two guys, right? Final is negative, or final is positive, right? Because negative times a negative. Initial is just negative, right? So that's why it's in this order. And then we have all these constants out here. We can absorb this into here, right? Because this guy is this guy are these guys. Absorb this into here, we get this. This here is Rydberg's constant, RH, and we rewrite this as this. So this is Rydberg's equation. What it tells us is that we can calculate the wavelength of this, calculate the wavelength of that by this equation. All we need to know is the energy levels, and actually, this should just be squared. The Rydberg constant is one of the most accurately known physical constants that we know of, and is this guy right here. 10,973,731 meters, and we can convert that however we want to, between metric conversions and all that. All right, so what we've been going through is this idea that particles, or energy, is quantized, okay? We could think of light as being quantized, or in sort of these small billiard balls. And in doing that, we are able to accurately describe blackbody radiation, accurately describe the photoelectric effect, and come up with accurate numbers involving how hydrogen emits wavelengths as it absorbs wavelengths. But then there's this snafu, and right, the snafu is the idea of particles also having a wave-like nature to them. And you can ask the question, well, okay, how can a billiard ball be like a wave? Well, this is where Louis de Broglie really established his insight. What he said was that everything has a wavelength. We know from the double slit experiment that electrons have wave-like qualities to them. And what he said basically was that everything behaves like a wave. It's just more evident when the object has very low mass. And so he developed this equation. As the mass of some object increases, the denominator here is going to increase, effectively making the wavelength a lot smaller, right? So I have a huge mass relative to an electron. My wave-like properties are going to not be very evident, right? Because I'm a very massive object. An elephant is a very massive relative to something really small like an electron. The smaller and smaller we get, the more wavelength something is going to have, the more wave-like something is going to be. So the wave-like nature of fundamental particles is modulated by an applied voltage. And the best way I like to think about this, coming from a biophysics background, is that when we do cryo-EM, we want to really exploit the wave-like nature of this, right? So suppose something is massive, okay, we can still get a wave-like property from this if the velocity is really freaking big, right? So we use these applied voltages to accelerate particles to high speeds, super high speeds, to get this wave-like nature from them. And in cryo-EM, you get something akin to a scattering effect when you throw electrons at proteins, and that's exploiting their wave-like nature, okay? So it's not really scattering, it's interference, right? It's wave-like interference whenever you're throwing electrons at something, okay? And so this is going to move us on to the next chapter. We want to understand waves, so we're going to get into the classical wave equation. One thing that I didn't note here is that whenever electrons are, there's the different types of series, there's names of people that sort of correspond to what energy levels these electrons come from and are going to. Like the Lineman series, the Balmer series, and all this stuff. I didn't put that in here. You can look those up if you want. If you want me to go over those in a separate video, I can do that as well. But again, I want to go a chapter per week. So if I make a video between now and the next chapter, it'll be on the Balmer series or something like that, or it might be doing an example problem or something like that. So with that being said, that is chapter 1. Again, we're going over Physical Chemistry, a Molecular Approach by McGuire and Simon. And so make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.